Right. Thank you so much. You're setting the bar very high for this presentation. So let me see if I can meet that bar. So it's a true pleasure to be here. Thanks for having me, and thanks for attending the talk. As she has said, I'm Luca Carlone. I'm an associate professor at MIT. And the goal for today is really to share some of the ongoing work my group is doing on going towards certifiable spatial perception systems and algorithms. So maybe a good way to start this presentation is just to tell you a little bit about my group. I'm the director of the Spark Lab at MIT. Spark stands for Sensing, Perception, Autonomy, and Robot Kinetics. And of course, we work in the broad area of robotics and autonomous systems, but we particularly focus on robot perception and vision-based navigation. So what you see in this slide are the three big research areas we are working on. We work on robust and certifiable perception. You're going to hear about these a bit in this presentation, ranging from problems such as visual inertial navigation, simultaneous localization and mapping, to problems like including object detection and pose estimation. Then we focus on high-level scene understanding, or what people in the community are calling spatial AI. I'm going to talk a lot about this today. And then there is one last research area, which I'm not going to touch today, is about co-design, is work at the boundary between perception and other areas of robotics, including control, communication, mechanical design, and so on. Is an area I'm super excited about. To have cool work on soft aerial manipulation. We just won Best Paper Award at Tyros last year on this. I just will not have time to go into the details of that. So before we even start with the technical contributions, I just want to start by saying that all the work that you're going to see today is really the result of amazing work done by students and postdocs in my group. So it's really this is to give credits to them for putting so much effort and for getting cool results out of their research. So the plan for this presentation is really to cover two big ideas. I want to cover the work we're doing on what we call spatial perception systems. This high level is just an effort to go from traditional mapping in robotics to real-time 3D scene understanding. So the first part is mostly going to be high level and about systems. So you're going to see a lot of system work. But then in the second part of the presentation, I'm going to zoom in on the algorithms. And the second part is going to be a little bit more mathematical. Not too much, but I'm going to zoom in a little bit on the algorithms. And then, of course, I will conclude and discuss open problems. So the size of these boxes are reflecting a bit what is the duration of each part. I'm going to spend most of the time on the first part. Then I will jump in for maybe 10 or 15 minutes to this, and then I will conclude. So let me start by discussing the work we are doing on spatial perception. And again, this effort of going from mapping to real-time 3D scene understanding. The basic motivation for this work and for our effort in thinking about real-time 3D scene understanding is the realization that there is still a large gap separating robot perception from human perception. Over the last decade, we have made impressive progress in robot perception. For example, right now we have good algorithms for geometric understanding. Thanks to the progress in simultaneous localization and mapping, we have really real-time algorithms that can process sensor data and build in real time, without prior knowledge, a 3D geometric model of the environment, such as a large-scale point cloud or a voxel-based representation, for example. At the same time, with deep learning, we made impressive progress in 2D semantic understanding, right? We have algorithms and architectures such as YOLO, which are able to detect bounding boxes of objects in the images, or we have even networks to do pixel-wise segmentation, as the one that you see in this image, in which for each pixel, we're able to assign a semantic label to the corresponding pixel. At the same time, we have to realize that as humans, we do much more than that. And to convince you that human perception is much more than just geometric understanding and a bit of semantic understanding, I just have to show you a single picture. Okay? So as a human, if you stare at the picture on the right for a few seconds, you can quickly understand what is the geometry of the scene, right? You can understand that there is a road, there are buildings. You can understand what is the semantic of the scene. For example, there are cars, pedestrians, and you can also reason over the 3D location of these objects. And you can think about relations within different objects. For example, you can think about the fact that the car is driving on the street or that the car is approaching the traffic light. So this kind of 3D scene understanding, which is capturing at the same time geometry, semantics, and relation in a very holistic way, is something that is still missing for robotics. Well, but the question is, why do we care about this in the first place? Why is this kind of 3D scene understanding important for robotics? And I'm going to argue that the reason is twofold. First of all, high-level 3D scene understanding is key to interaction. If our robot is only able to understand geometry, our robot is doomed to execute low-level geometric instructions. For example, the robot will be able to execute commands such as robot go to position X, Y, and Z. But personally, if I have to picture the next generation of robots, I would like for them to be smarter than that. I would like for the robots to be able to execute high-level instructions, such as robot, go grab me the cup of coffee on the table in the kitchen. And for the robot to parse and execute this complex instruction, the robot will need to know about geometry, right? We need to know how to get to the kitchen. We need to know about semantics. What is a cup of coffee? What is the table? And we need to reason over relations. What does it mean for the cup of coffee to be on the table and for the table to be within the kitchen? So 3D scene understanding is key to interaction. Even more so, high-level scene understanding is key to robustness. In particular, I'm going to argue that any robust perception system must reason over geometry, semantics, and relations in 3D. And I'm going to give you just a simple example. For instance, imagine that I show you this image, this slide, and I just try to detect an object, detect the car in this image. Of course, I can detect the car. But if then I look at the broader context surrounding the image of the car, I realize that in the middle of the image, this is not a physical car, right? This is a picture of a car on the billboard. And this conclusion is easy for human perception because as humans, we reason over geometric cues. For example, we reason over the fact that this car is too far from the road to be a physical car. We reason over the semantics of this object, which is a billboard. And we also reason over the relations between the billboard and the car. Essentially, the billboard and the car cannot occupy the same physical space, therefore one should be painted on the other. Okay, so correct scene understanding is really relying on simultaneously understanding geometry, semantics, and relations in 3D. So you may argue that actually this kind of specific images are not going to trick modern perception systems, but I can provide two examples to tell you that actually modern perception systems are not really as advanced as you might think. And just by chance, like by coincidence, both examples are from Tesla. This is one from June 2021. And what happens is that the autopilot is detecting a bunch of traffic lights, right? But if you look at the actual scene, what happens is that these are not physical traffic lights, but they are just traffic lights which are carried by a truck. And of course, for the perception system to correctly understand the scene, the perception system must reason over the relations between different objects, must reason over the relations between the traffic lights and the truck, rather than doing just object detection in isolation. And of course, if you look at recent news and the news about phantom braking from Tesla, you really realize that the state of the art in perception systems is really far from the type of robustness that we get with human perception. So the first contribution that I want to cover today is really the work we are doing on designing spatial, really the first kind of spatial perception systems for 3D scene understanding that are able to reason over geometry, semantics, and relations in real time. And I'm going to provide kind of a sequence of systems of increasing complexity, starting from early work on Kimera, which many of you have seen already, to very recent work called Hydra, which we just released a couple of weeks ago. And it is actually the first time I'm going to present the results of these systems. So, but let me start with Kimera. Kimera is an early attempt at doing essentially reasoning over geometry and semantics at the same time in real time. So what is Kimera? Kimera is a system which is taking as input sensor data from a standard camera. So there is a sequence of images as well as inertial data. There is an eye on the camera. And as output, Kimera is building what is called a 3D metric-semantic model. So what you see here is not just a plain video, is a 3D model in which the geometry is described as a mesh, as a 3D mesh. And each phase of the mesh is colored by semantic label. So for example, gray stands for ground, dark green corresponds to the walls, light green to the chairs. So each color is a different semantic label. And what I want to do in the next couple of slides is really give you just a big picture about what's inside Kimera and tell you about the latest experiments that we've been making with this system. Probably the first order information here is that Kimera is open source. So if you want to try this for yourself, you can just go on GitHub and try it out. Everything is open source. You have a good and fast implementation. So how do we get this kind of metric semantic mapping capability? Well, Kimera is taking sensor data as input, as I said, and the first thing that we'll try to do is that we'll try to reconstruct the trajectory of the robot moving in the environment. Remember that in this kind of systems, we assume no prior knowledge of the environment, so the robot is starting from scratch, building a map of the environment. And the first step is what is called visual inertial odometry. Essentially, Kimera is solving an optimization problem to reconstruct from images the trajectory of the robot moving in the environment, and is also reconstructing the 3D location of points, which you see in green, which are observed in the image. So this is based on something that is called IMI pre-integration theory, which is something that we developed a few years ago at this point. And the result of this module is really an odometric estimate of the trajectory of the robot. This odometric estimate is then passed to a second module, which is called Chimera Semantics, which will be in charge of building this map around the trajectory estimate of the robot. So the mapping part is just a Bayesian inference over a voxel-based representation. And the inference is both about inferring the occupancy state of the voxel as well as a semantic label for the voxels. And after this voxel-based representation is built, then it can be quickly converted into a mesh using standard algorithms such as marching cubes. The thing that really stands out for Kimera is that all of this mapping is done in real time on a CPU-based parallel implementation. So we're not using too much computational resource in this case, just because it's a pure CPU-based implementation. And finally, what happens is that the odometric estimate will drift over time just because it's a source of odometry, right? So we have a final module, which is Kimera post-graph optimization, or better, robust post-graph optimization, which is in charge of correcting the trajectory in response to loop closures. So for those of you who are not working in SLAM or perception, what it means, what is a loop closure? Imagine that the robot is navigating the environment, and what you see is the odometric estimate of the trajectory, which accumulates error over time. What happens is that at two different times, the robot might be seeing the same portion of the environment. So maybe is seeing part of the kitchen at this pose and part of the kitchen at this other pose. And this allows to create kind of these loop closure constraints, which are enabling a correction of the trajectory. So let me play this again. The trajectory, the odometric trajectory is drifting over time. And if you're able to detect these loop closures, you can correct the trajectory and make it more accurate. So what really stands out in Kimera is that we have an approach for doing this correction, which again is called post-graph optimization, which is really robust to outliers, because in practice, many of these loop closures are produced by place recognition techniques, which are really prone to failure. And in Kimera, we have robustness to outliers, which is enabled by one of the certifiable algorithms I'm going to discuss in the second part of the talk. And on top of correcting the trajectory of the robot, we also have a new technique. I'm not going to discuss that too much, but we have a technique to also correct the 3D mesh in response to loop closure, which is a method that we call post-graph and mesh optimization. So that's one slide overview of Kimera. Everything is running on CPU here, and everything is running in real time. And hopefully, we're going to have a release 2.0 of this library later this spring. What I want to do next is really to showcase some of the recent results we have in deploying these systems on both simulation, photorealistic simulations, and real data. And I'm going to showcase actually one of the challenging results or challenging demonstrations in which we are even running Kimera simultaneously on multiple robots. So we have 3 robots. In this case, they are driving in simulation, and they're estimating their own trajectories that you see in yellow is not super visible, but they're also building this metric semantic mesh in which each color corresponds to a different semantic class. Okay? And when the robots are creating these loop closures. Maybe when the robots are meeting each other, they perform this post-graph optimization to correct the trajectory and potentially correct the mesh. So this is work done in collaboration with the group of John Howe. And for those of you who don't believe in simulation, we have also very cool real experiments with KIMAERA. Still, in this case, I'm showing just for fun an experiment with 3 robots running KIMAERA. And I'm starting to show just the trajectory estimates. The trajectory estimates will drift because of the visual inertial odometry will drift over time. But as long as there are loop closures, whenever there is a loop closure, the trajectory gets corrected. And the result is that the trajectory gets better and better over time, which is something that you see qualitatively in the video, but also you can see in the numbers, like in the table. These are localization errors or trajectory estimation errors in meters. The VIO errors are quite large because these are very long trajectories, but after loop closure, you can reduce the error by a large amount and you can get an error in the order of centimeters at this point. The last part of this video is also showing the post-graph and mesh optimization, which is a cool aspect of KIMAERA in which you deform and you correct at the same time both the trajectory of the robots as well as the mesh reconstruction around the robots. And you can see that whenever there is a loop closure, the mesh constructed by the 3 robots gets corrected and deformed more and more until it converges to a nice 3D reconstruction of the environment, as it happens like at the end of the result. Okay, so we have this approach, which in this case is without semantics, but KIMAERA in general is a metric-semantic SLAM library that is running in real time. And this is work that we have done over the last few years. But when we proposed this technique a while back, we realized, okay, this is great, this is real time, works nicely, but we also realized the fact that the type of mesh representation that you get out of KIMAERA is not necessarily the best representation for robotics. First of all, it's kind of difficult to do planning. Essentially, with this representation, it's difficult to do motion planning, for example, over a mesh. And this representation is also quite large, so maybe it's not really allowing to capture all the information. Is not even capturing relations among different objects, which is one of the motivation we started from. We wanted to capture also relations, geometry, and semantics. So this motivated us to go towards the second idea, which is the idea of 3D dynamic scene graphs. 3D dynamic scene graphs are essentially a hierarchical map representation, is a new type of map representation, which is storing, which is modeling the environment as a graph. And what I'm going to do here is to explain the video in a second, the video on the left, and then we're going to go together through the details on the right. So what is a 3D dynamic scene graph? Is a graph, hierarchical graph representation in which there are multiple layers. And the basic idea is that at the lowest layer, you have just a metric-semantic mesh, which is the same that you got with KIMAERA. But the more you go up in the layers, the more you abstract away the low-level geometry into high-level semantic concepts. For example, at layer 2, you capture objects and agents, right? Without worrying about the entire mesh, you just isolate objects and agents. At layer 3, you detect places and structures. Places essentially are collision-free location the robot can move to, while structures are ceiling, walls, and so on. And then you can go up for indoor environments into segmenting rooms, buildings, and so on. So more formally, a 3D dynamic scene graph is a directed graph where nodes represent spatial concepts and edges represent spatio-temporal relations within concepts. So why this is a powerful representation? Well, first of all, we finally are able to capture relation among different objects, which we saw was a kind of a key to high-level understanding. Second, for those of you who are familiar with mapping for robotics, this representation is unifying metric maps, such as the mesh at the bottom layer, with topological maps. So the graph of places is just a topological map of the environment. Moreover, this kind of representation is starting to capture objects, rooms, buildings, places. So this representation is really suitable for motion planning, task planning, and just decision-making for robotics. So something that I must say when giving a talk at Stanford is that actually pioneering work on 3D scene graph comes from Stanford. So the first paper on 3D scene graphs is from the group of Jitendra and Silvio Savarese at MIT, was led by Hiro Armeni. And what we are doing here is to propose a version which is more geared towards robotics. So we're changing a little bit the structure to make it more useful for robotics. And we are developing real-time algorithms to infer this kind of representation in real time from sensor data. So in terms of building this representation from sensor data, the first attempt we tried was what we call Chimera VSG, Chimera Dynamic Scene Graph. And I will tell you high level what Chimera VSG was doing. And I will conclude that this actually was not a real-time approach. And this will motivate me to propose to describe the last system, which instead is going to be a real-time system. But let's look at this first attempt. So in the first attempt to build a scene graph from data, we essentially used sensor data. We fed that to Kimera to build layer 1, which is the metric-semantic mesh. But then we also added algorithms to build the other layers. For example, we added algorithms to build layer 2, which is the layer of agents. And we did that by mixing deep learning, image-based human pose estimation with deep learning, with post-graph optimization for tracking of humans over time. And the result is what you see in this video. We're able to detect dense models of humans moving in front of the robot, and we're able to track the motion of humans as they move through the environment. Moreover, we're also able to isolate objects and detect objects as part of the mesh. The detection of the object depends on whether we have some shape information about the object or not. If we do not have shape information, we just fit a bounding box. If you have some shape information for the object that we are detecting from the mesh, we just do some registration algorithm, which is one of the algorithms, certifiable algorithms I'm going to describe later in the talk. And finally, the scene graph also has places and rooms. The places are really just forming a skeleton of the environment. So what is the graph of places? Is a graph in which nodes are free space location and edges represent traversability from one place to the other. And in order to reconstruct the places here, what we do is that we take a voxel-based representation and we just compute what is called a generalized Voronoi diagram to extract this graph of places. And then we do some, graph clustering algorithm. We'll get there. We do some graph clustering algorithm to isolate the rooms from the graph of places and to cluster the different rooms. So with this initial system, Chimera VSG, we already got very compelling demonstrations of building 3D scene graphs from data as the one that you see in this video. The main issue with this system is that we were able to build scene graphs, but it took several minutes essentially to build. The scene graph was not compatible with real-time operation. And there were two quite fundamental challenges to solve to make this into a real-time system. The first challenge is that to build the graph of places and to segment the rooms, essentially our first system relied on processing of a monolithic voxel-based representation, a huge voxel-based representation of the entire environment. And that kind of processing of a large voxel-based representation was not compatible simply with real-time operation. And then the second challenge is that remember that when your robot is navigating in real time, keeps getting these loop closures and keeps correcting the trajectory, its own trajectory estimate in response to loop closures, which means that whenever you have a trajectory change, you will need to reconstruct the scene graph from scratch. Or at least with the first approach here, we will need to reconstruct the scene graph from scratch, which is simply incompatible with real-time operation. So this brings me to the last system I want to discuss today, which is something that we proposed and we released online a couple of weeks ago, which is Hydra, which is the first system for constructing 3D scene graphs from sensor data in real time. Here, what you see is the architecture for Hydra. I don't want you to parse all the details of the architecture. I just want to give you a couple of insights about what's inside this architecture. And the first insight is that 3D scene understanding really involves asynchronous perception processes running at different rates. For example, if you want to do 3D scene understanding, you will have to do some image processing and some low-level perception tasks, which have to run very fast, and they're just running at sensor rate. You have to combine these with tasks such as, for example, mesh reconstruction or visual inertial odometry, which are what we call mid-level perception processes, which can run a little bit slower and can reason over a short time horizon. And then you always end up having high-level perception processes which have to reason over the entire map, and somehow they must be slower because they have to reason over the entire map. So really, because of this presence of multiple perception processes which are asynchronous, that are running at different rates, a key tool that you have to deploy is that we have to make our perception system highly parallelized, just to enable real-time operation. The second challenge or insight is that, again, we cannot really hope to rebuild a 3D scene graph from scratch after loop closure, because that will really prevent real-time operation. And to avoid building a scene graph from scratch after loop closure, we propose a new technique, which we call 3D scene graph optimization, which is just correcting the scene graph every time there is a loop closure in the trajectory of the robot. So let me show you a couple of features of Hydra. First of all, I want to show you how this works when building incrementally the scene graph. Hydra will use something that is similar to Chimera in building a metric-semantic mesh of the environment, but at the same time, we'll just keep a voxel-based representation around the robot position. We'll never reconstruct an entire voxel-based representation. At the same time, from the mesh, we'll extract in real time the objects, and we fit bounding boxes to the objects. And then when it comes to the places, we'll use some byproduct of the integration of the voxel-based representation on the fly to reconstruct the graph of places, which again are forming a topological map of the environment. And then we apply a community detection algorithm to cluster the graph into different rooms. And you can see that the rooms here in red and magenta or violet here are matching the two rooms in the reconstruction. So to enable these, again, we have new algorithms based on community detection, as well as a highly parallelized architecture. But really the technical aspect of Hydra that I want to showcase here is this idea of 3D scene graph optimization, which is optimizing the scene graph in response to loop closures. So imagine that you have your robot, which is building a scene graph, including the poses of the robot, the graph of places which are in blue, and is reconstructing some 3D mesh. And imagine that the robot at some point gets a loop closure as the dashed line that you see over here. The basic idea here is that in response to this loop closure, we can solve a single optimization problem, which is trying to recompute the position of the vertices of the mesh, as well as the position of the places and robot, such that we essentially accommodate the loop closure while avoiding to deform the geometry of the scene too much. Okay, so we just solve a large optimization problem. And actually we do that using an old technique from computer vision, which is called deformation graphs. Deformation graphs is essentially sampling the mesh into just a subset of vertices, and is forming a graph of different nodes, and we can solve an optimization problem to recompute what is the best location of these nodes given the problem constraints. For example, given the odometry of the robot, given the loop closure, and given some constraints on the local geometry of the problem. So in the paper, what we do is to show that not only we can solve this kind of optimization problem close to real time in a matter of few seconds, but we also show that this problem can be formulated again as post-graph optimization, which is again a standard problem in robotics. So you have existing tools that can solve this optimization problem very efficiently, and they're off the shelf. So let me show you just a real demonstration of Hydra, which I think is pretty instructive. So this is a real environment. We're using Hydra to map a student residence at MIT. The camera is going through 2 floors. So there is a floor 1, and there are the stairs, and there is a second floor. And what you see on the left are the images. Some of them are just removed if there is a person, just for privacy reasons. And there is a semantic segmentation from a neural network. And you see the 3D reconstruction from Hydra, the scene graph on the right, and a top view here on the left. And one of the parts which is more impressive to me is what happens. Let me pause this for a second. So you see that the trajectory is kind of drifting over time because, again, it's doing visual inertial odometry to estimate the trajectory, and that is drifting over time. But when the robot is coming back to a location that it has seen before, we'll essentially do this 3D scene graph optimization, and we'll correct the entire scene graph and the map reconstruction with a single optimization problem, which I think is pretty cool.
Can I ask one question, Luca?
Yes.
Yeah, so I was interested in exactly that moment, what happens and how this propagates over the hierarchy. And so I'm not sure if this is like happening only in the video maybe, but this loop closure, does this run in the background and you still integrate incoming information from the robot, and then how do you link this again to the maybe corrected loop closed map and all of this? How does that work?
It's a good question. Like, the secret here is really parallelization, right? You have to make sure that processes like the scene graph optimization, which is still fast but is running in a matter of seconds, does not have to interfere with the real-time operation. So there are multiple different threads. There is a thread which will correspond to a typical front end for SLAM, which is doing sensor processing in real time. And then there is this that every now and then when there is a loop closure, will get triggered and will solve this large optimization problem. And to make sure that things remain compatible, what we do is that we store an odometric version of the scene graph, and then we store an optimized version of the scene graph, and we make sure that these two are in sync, are synchronized every now and then.
Okay, thanks.
Very good. Okay. So we've been testing these on many data sets.
One more question quickly in the audience.
Yes, of course.
I have one question regarding, it looks like for now you're working with the single agent. Is a lot of your loop closures being done on the front end using like visual, like geometric reasoning methods, like perception aliasing?
Is the question if we get spurious loop closures, or what do we use to detect loop closures?
Yeah, kind of like what specific method you're using for your loop closures, like for your geometric reasoning techniques?
Yeah, it's a great question, because that's another contribution of the paper that I just skip over just because it's too much stuff here. You can do just image-based place recognition and loop closure detection with bag of words, standard approaches. What we do here is a little bit more. We say, first of all, we can detect hierarchical descriptors, right? If you want to do loop closure and you have a scene graph, now you can start telling the robot, not only you can provide the images, but you can also reason over the objects surrounding the robot, the geometry of the places surrounding the robot, the room the robot is moving in. So you can use all this hierarchy to make the loop closure detection much better. And indeed, what we do is to define a hierarchical loop closure. And then at the same time, when you have to reconstruct the relative pose for the loop closure, you can do a number of things. You can align the objects, right? You can align the images and so on. So I think a short answer to your question is that we define a suitable hierarchical descriptor to improve the loop closure performance over typical approaches based on image matching or feature matching. Okay, I hope that helped. And I suggest, really there are many more details, in the paper that I'm skipping over, but I just want to give you the big picture of how cool is this, or at least I think it's cool, as well as the results that we are getting on a number of data sets, both in simulation and real data. So these are the type of environments we tested in: office environments, apartments, subway, student residences at MIT. And we're able to do a good job at reconstructing these scene graphs. You're going to see a number of the scene graphs that we reconstruct here on the right. And we're able to reconstruct even scene graphs with multiple floors. You see that we have no troubles with stairs and so on, and we can still do a good job at segmenting the different rooms. What I want to stress here, just in the interest of time, the only quantitative result I want to stress here is the runtime. So I'm comparing here the runtime of Chimera VSG, which is the first approach I discussed, against Hydra. And you can see that Chimera VSG has just a complexity that grows over time because we review and revisit again and again the voxel-based representation. And so this will become impractical over time. And instead for Hydra, the runtime, again, is parallelized. So there are slow threads and fast threads. But for the fast threads, you can do all the processing in really a matter of milliseconds. Okay, let me wrap up this part. I really have to move on to the certifiable algorithms. What I told you so far can be understood if you visualize a picture in which you are plotting perception systems and you are looking at efficiency versus high-level understanding. I told you that the state of the art is really doing either geometric understanding or 2D semantic understanding. And we have pretty efficient systems which are not very smart. They're not providing high-level scene understanding. On the other end, we have things like HD maps, which will have a lot of information packed in, but they are human annotated, so they're not efficient. They're really run offline. And what we did is to really push the boundary of bridging the gap between current perception systems and human perception. We designed Chimera, which is an effort to bridge geometric understanding and semantic understanding. We proposed a first approach to build dynamic seeing graph, which was offline, so was not very efficient. And more recently, we have Hydra, which is both efficient and is getting to some sort of high-level understanding of the scene. So as you saw, most of the work I presented so far is really about systems. There are cool insights about algorithms, but I'm proposing these as really efficient implementation and putting together a number of perception problems in a single system. What I want to do next is to zoom in on some of the algorithms we use and discuss this idea of certifiable perception algorithms, because these algorithms which are running in the background of the perception system I discussed in the first part of the talk are really the reason why the perception systems we are building are working and they are robust. So this part is going to be a little bit more mathematical, but again, I will try to give you the ideas without throwing too many questions around. So the first observation is that a complex perception system requires solving many perception problems, including, for example, object detection in either point clouds or from images, as well as, for example, the estimation of the trajectory of the robot, which is something that before I called post-graph optimization. So for a perception system, we have to solve all these challenges. The nice opportunity here is that despite the diversity of these problems, from object detection to pose estimation here, in the background of this perception problem, you end up solving some optimization problem. And that's a commonality across all these perception problems. So the type of optimization problem that you end up solving is something like this, in which you're trying to estimate a quantity of interest. Let's say the X, for example, is the pose of the car that you want to localize. You are given a bunch of measurements, yi. For example, the measurements are, feature detections that you have from the image. And you're trying to find the X, which is minimizing the residual errors. The residual error is a given function, which is quantifying how well your estimate is explaining the measurements. And of course, in practice, you're going to have a large set of measurements that you're given. So this is a very general formulation for a bunch of perception problems. The unfortunate thing that is preventing robustness, is making existing system brittle, is that in practice, there are going to be many measurements yi, which are outliers, which are completely wrong. For example, if you're doing feature detection and you want to estimate the pose of this car, some of the feature detections may be completely wrong. And if you're solving this optimization problem with outliers, you're going to get a bad estimate for the X. So of course, we are not the first to encounter problems with outliers. What we can do is just look at the literature on robust estimation. And people in robust estimation will tell us that the solution to reducing the impact of outliers is to put a robust loss function in front of our residuals. Instead of minimizing the squared norm of the residuals, we can minimize a robust loss function rho. And so we have this general recipe to have to solve perception, these optimization problems arising in perception in the presence of outliers. And my question is then, why the state of the art is still brittle? Why the state of the art is still suffering from these outliers? Well, the reason is simple. People in robust estimation theory, they told us how to formulate the problem, right? This is how to estimate the X in a robust way, but they didn't tell us how to solve this optimization problem. And what happens is that for common choices of robust loss function rho, for example, this is a popular one, which is a truncated least square loss. What happens is that the cost function is non-convex. This is a non-convex function. And therefore, the overall optimization problem is a non-convex optimization problem. I'm sure many of you will be familiar with optimization, but essentially non-convex means that there are multiple valleys here. And if our algorithm is able to get to the bottom of this cost function, we'll get a good estimate for the variable we care about for the position of the car. If the algorithm instead is stuck in some local minimum, the estimate for the location of the car is going to be poor. So I can summarize the state of the art really in a couple of sentences here. the state of the art is split in the state of the art in solving this optimization problem is split between local solvers, which you can think about, for example, as gradient descent, Gauss-Newton, and so on, which rely on some initial guess and also are easily stuck in local minima. So that's why they are brittle. On the other hand, you can use techniques like ransack, which are going to try to get to the minimum of the cost function by sampling the measurements that you are given in the problem. But unfortunately, ransack will still fail with high probability if you have many outliers. And for those of you who have played with ransack, ransack really requires a minimal solver, so it's mostly suitable for low-dimensional problems. And a shortcoming of both local solvers and ransack is that they will give an estimate for the quantity you care about, and this estimate can be completely wrong, but they will not be able to detect the failure. So they will both fail without notice. So what you've done over the last few years is really to think about this idea of certifiable perception algorithms. And in a sentence, certifiable perception algorithms are algorithms to solve the robust estimation problems that I had in the previous slide, like this optimization problem. And we want to solve these optimization problems to optimality in polynomial time or declare failure. So either we solve the problems efficiently, or if we cannot solve the problem, we want to detect that we are not able to resolve the problem. And this, just full credits, this is work led by my student Hank Yang, who is on the job market this year, and he's just doing terrific work, has been doing terrific work on this research line. So for this, I want to jump a little bit more into the math. So I'm going to have 2 or 3 slides which will have equations, but hopefully you will see some very simple message out of these slides. And I want to tell you what is the general philosophy that we use in going from these robust estimation problems, as the one that you see at the top of the slide, to polynomial time algorithms. Essentially, the insights that we had are just twofold, they're very simple. The first one is that a large set of robust estimation problems in this form, and in particular those arising in robot perception, can be formulated as polynomial optimization problems. So for those of you who don't know what is polynomial optimization problem is nothing else than an optimization problem in which both the cost function and the constraints are polynomials. So P, H, and G are just polynomials in the unknown X, okay? And we can have both equality constraints and inequality constraints. So the first insight is that we can rewrite this cost function, this problem, as a polynomial optimization problem for a large class of perception problems. And the second insight is that once you have a polynomial optimization problem, there is a very systematic way to get a convex relaxation, what is called a moment semi-definite relaxation for the original problem, which is going to solve the problem for us in polynomial time. So what I want to try today, for the first time, I want to try to have a proof sketch, actually, for the first point. I want to show that it's actually simple to convert this problem into something that is a polynomial optimization problem. And I want to tell you a little bit about this idea of moment relaxation, again, with a single slide. So I'll do my best just to give it the bottom line. So, but let's start this exercise of converting this problem into a polynomial optimization. So again, the proof, or the thing that I want to prove with you today, is that I can convert. The statement is that this problem is a polynomial optimization problem for common perception problems and for several choices of loss functions. I will be a bit more precise in a second. And the way I'm going to prove this statement is in 3 steps. First of all, I'm going to claim that the residual error squared, so R here, the residual error squared, is a polynomial in X for many perception problems. And this is something that can be just proven by inspection. So if you look at the common perception problem, for example, object detection from point clouds, 3D registration, absolute pose estimation, and many others, you will look at the structure of these problems, and these typically have some quadratic objective, or they have a linear residual, and of course will become a quadratic function after you take the norm squared. Why is that? Why is so common of a pattern in these problems? The reason why is that the action of rotations and translation is linear, right? And most of these problems are just rotating quantities around in different reference frame. And again, rotation and translations are linear operations. Therefore, the resulting residuals will be just linear functions, and the square residuals will be quadratic functions. So we proved that the R squared is a polynomial. Now we have to prove that the domain, like the constraints here, which is this X, is also can be described as a set of polynomials. And this is as simple as saying that typically these problems involve just reasoning over translations and rotations. Translations are just vectors, so they are unconstrained. And instead, rotations are member of SOD, the special orthogonal group. And the expression of the special orthogonal group can be written as a set of quadratic equality constraints. So both these constraints and this, which is the definition of rotation matrix, can be described as quadratic equality constraints. So in other words, typical constraints involving translations and rotations can be written as polynomials. And it is also true for other type of constraints, for example, field of view constraints, distances, and so on. So far I proved that these X here can be written as polynomial constraints. These R can be written as a polynomial. The only thing I'm left is to reason over this rho. And I'm going to show that also the rho for 7 popular choices of robust loss function can be written as a polynomial. So the claim here is that the robust loss rho can be written as a polynomial in the square of the residual by introducing extra variables for 7 robust cost functions. And really, the proof is relying on this idea of Black-Lagrangian duality, which is saying that this optimization problem, where rho is a robust loss function, is equivalent to this optimization problem, in which essentially for each measurement, you're adding a scalar weight, which you can understand as kind of a measure of confidence over that measurement. Do you trust the measurement or not? And again, there is this Black-Lagrangian duality is providing us a very systematic way to move from this formulation to this formulation. In the second formulation, you see that as long as R squared is polynomial, the first term is a polynomial. And for 7 robust loss functions, also the second term is a polynomial. Robust loss functions are truncated least squares, maximum consensus, German-McClure, Takei, and Huber. So many popular robust loss functions will end up leading to a polynomial. So hopefully, so far, with this very fast proof, I just tried to convince you that this problem can be written as a polynomial optimization problem. What I want to do next is to tell you that there is a very systematic way to get a convex relaxation to these polynomial optimization problems. And this is something that if you haven't seen in the past, I suggest you really to take a look at, because it's a very powerful tool, which is called Lasserre moment relaxation. So imagine that you're starting from a polynomial optimization problem. These are tough problems. They're non-convex. They're hard to solve in the worst case. What Lasserre is telling us is that we can do a convex relaxation of this problem. And the first step is to define a monomial basis. Monomial basis is just a collection of monomials. In this case, I have just 2 variables, x1 and x2. I just have all the monomials of order 0, order 1, and order 2. And then I can define a moment matrix, which is just the monomial basis as a vector multiplied its transpose. And even if you don't understand the details, what you have to think about is that the moment matrix is just containing all the monomials of given order, for example, from order 0 to order 4. And the basic idea is that every polynomial here, assuming that these polynomials are of order less than 4, can be written just as a linear combination of monomials, therefore can be written as a linear combination of these metrics. So in other words, you can rewrite both the problem objective and the constraints as a linear function of the x and as a linear constraint in the x. Of course, the x is not an arbitrary matrix. It has to be positive semi-definite because of this relation and has to be rank 1. But the basic idea in the relaxation is that we just keep the positive semi-definiteness constraint because that's convex, and we just drop everything else which is non-convex. And as a result, we get the convex semi-definite program, which is this one, which being convex can be solved in polynomial of time. So look, we relax the hard non-convex problem into a convex relaxation, which can be solved in polynomial of time. So presented like this seems like just heuristic. The thing that is making Lasserre relaxation very interesting is that there are very strong theoretical results telling you that the relaxation in many cases will get the right solution. It's not going to get you an approximate solution, it's going to get you the exact solution to the problem you relaxed. I don't want you to read all the details on the theorem. I think the theorem is telling two things. The first one is that if you make the matrix X large enough, this relaxation is always going to be exact. So in other words, if the matrix X is large enough, you can always solve this problem, again in polynomial time. And from the solution of this problem, you can compute a solution to the original non-convex problem. And we tell you also something different. We tell you that whenever you solve this problem and you get a rank 1 solution, so the X is a matrix, whenever the matrix has rank 1, from that matrix, you can reconstruct a solution which is guaranteed to be optimal for the original problem. Okay, so there are very strong mathematical guarantees. And what we notice in practice, which is really motivating us to use these tools in perception problems, is that we get rank 1 solutions. So we get exact relaxations even when the size of the X is pretty small. So in technical terms, the relaxation is tight or exact at the lowest relaxation order kappa, where the kappa essentially is controlling what is the size of the X. Okay, so we transformed a problem which is hard in general into a problem that can be solved in polynomial time. And we see that for modest dimension of this problem, we can already get optimal solutions to the original problem. So this is the technical insight. Going back, resurfacing a little bit to the big picture, what this technical insight enabled us to do is to design really a toolbox of perception algorithms to solve a broad variety of perception problems. So right now we have algorithms to solve from pose estimation in point clouds, images, and trajectory estimation problems. And we have a number of algorithms to solve that. I'm not going to get into the details, these are graduated non-convexity and Robin are two of the algorithms, but also we have a technique based on this idea of convex relaxation to certify that a given estimate is correct and is optimal, or to discard an estimate as suboptimal. That's really the idea of certifiability. So just I'm running out of time, we'll not tell you, we'll point you to the papers for the details. I just want to tell you, in terms of results across many problems, we have a number of algorithms that we applied to a bunch of different perception problems. For some of them, we also have open source implementations. And the result is that we have algorithms which are able to tolerate an impressive amount of outliers. For example, you can do object pose estimation from point clouds. Even in the presence of 95% of outliers, we can get right results. We can estimate pose and shape from point clouds and be robust to a large number of outliers. Estimate pose and shape from images, of objects from images, and get robustness to 70% of outliers. And estimate, solve robust post-graph optimization problems and be robust to, again, large number of random outliers, which is really enabling our perception systems to work robustly in the presence of, for example, bad loop closures, as I mentioned before. So I'm running out of time. Actually, we skip the last few slides and I will jump into the conclusion open problems. And I will just go fast through these to make sure that we have a little bit of time for questions. I'm going to tell you in the next couple of slides what's missing. So far, a lot of work we have done is about getting certification for these model-based algorithms, which are solving optimization problems. And at the same time, we design very sophisticated systems, right? What is missing really is how to get certification, not at the algorithmic level, but of the entire perception system. So the first big open problem that we're thinking about is how to get performance guarantees for perception systems, not algorithms, but systems. And you can think about perception system as including a bunch of different algorithms, which are maybe optimization based or are based on deep networks. The question is, if you have a complex intertwining of algorithms, how can you get some performance guarantees? And you can break this down into two questions. For example, you can ask, can we detect if algorithms are failing, are producing correct results, including both model-based and learning-based algorithms? Or we're also thinking about just a priori guarantees. Given a certain architecture, can I quantify what is the maximum number of failures that I can detect in that architecture? So big question, system level certification. The other big question is really how to use the results that I presented today about certifiable algorithms for optimization, and really use the certifiable algorithms to kind of self-supervise or produce certification for learning-based methods. So today what I told you is that given a bunch of feature measurements, I can solve an optimization problem and I can get an estimate, for example, of the pose of the car. But the truth is that these measurements are typically features detected by a deep network, right? So what we are really investigating right now is how to feedback this information from our robust estimators into the neural network. And through this feedback loop, we really hope to get some self-supervision and hopefully to get some performance guarantees on the performance of deep learning-based methods. Okay, so in the interest of time, I will just wrap up. I think today, I just told you about the fact that the next generation of perception systems really requires, hopefully I convince you that it requires high-level 3D scene understanding, including geometry, semantics, and relations in real time. And I told you about different systems towards that goal, including Chimera, this idea of 3D dynamic scene graphs, and the recent real-time effort on Hydra. And I also told you that to get real robust perception, we also need better optimization algorithms to support different perception tasks. And I propose this mathematical idea of certifiable perception algorithms, showing you just a few applications to real problems. And I quickly listed a couple of open problems about system-level certification and how really to extend certification to learning-based algorithms. So we'll stop here, hoping that there is some feedback, comment, or questions. And we stop by just thanking the sponsors supporting this work and just thanking you for your attention. It was really a lot to digest the presentation. I hope that there was some nice takeaway at least.
Yeah, thank you so much, Luca. Are there any questions? Yeah, go for it.
Hi, great work. I wanted to ask about your work on certifiable perception. How does the complexity of the algorithm depend on the input dimension? Since it relies on solving SDPs, I was wondering about this.
Yeah, the size of the SDP, it's a good question. There are multiple answers. The first answer is that the size of the SDP, I don't know if I can get to the slide. I don't think it's super useful. The size of the SDP will grow with measurements because you have a decision to make about each measurement being an inlier or outlier. So we'll grow at the same time with the number of measurements, and we'll also grow with the size of the X, with the variable that you want to estimate. And at that point, how to solve the SDP? There are lucky cases in which you can, the SDP will have some specific structure which is amenable for fast algorithms such as the Riemannian staircase. You can solve really those in real time. For some other cases, you do not have much structure. And we also propose different algorithms to solve the SDPs in a little bit of a faster way to leverage the fact that you know that the SDP is going to have a rank 1 solution. So you can leverage that information to develop a little bit of a faster solver. But in general, you have to be careful, the SDP, some algorithms, maybe that's a good way to summarize this. In this toolbox, really, some of the algorithms are completely running in real time, like Robin and graduated non-convexities are fast algorithms. But if you don't really want to get the certification and you want to solve the large SDP, you need to pay a little bit of a computational price. So these two are real time, are running completely in real time. This one requires a few seconds to run, so it's not real time yet. There is much more to say. The SDP ideas is not only used, as I said, for the certification, but is also used as smaller size SDP is also used in these other algorithms. But that's a longer story. I would suggest just to look at the references to get a little bit of a deeper answer.
I have a little follow-up question, which is, so if you look at the map in the bottom left of the truncated least squares box, the map is probably some kilometers across, right? And I'm curious if there are any numerical challenges, because if you usually scale things down to the -1 to 1 box for polynomial optimization, Or maybe there's some tricks where you can get around some numbers being very, very small and some numbers being very, very large when you actually have to solve these optimization problems.
I understand that the question is about numerical conditioning of algorithms, but I don't understand if this refers to this optimization problem or to which one. So I think you're referring to this one, maybe like to this idea, right? This one. I don't know, I don't know if the numerical conditioning is the biggest problem for this. I think that something that, of course, is difficult to see from this slide is that there are a couple of things which are making these problems difficult to solve. And the first thing is that these are what are called degenerate SDPs. So the degenerate SDPs, at least the way I understand it, is that for a choice of primal variable, there is an infinite choice of dual variables which are optimal. But anyway, there is some degenerate in the SDP, which is preventing you to use standard tools for solving these SDPs. And the other challenge is that you end up having many, many constraints. So the size of X is actually not the huge problem, is the fact that at the end of the day, you're going to have a large number of constraints, which are making the solution of this optimization problem a bit slower. These are the main challenges that we have seen. And if you're curious about what you have done just in terms of solving the SDP problem, you can look at a paper which is called Stride. That's an algorithm that we propose to solve this type of optimization problems. And inside there is that if you try to solve the SDP in isolation, for example, I don't know, you can do some projected gradient descent on the SDP, right? So it's a slow algorithm, but you can do it. You are not really exploiting the structure because essentially this problem is a relaxation of a much lower dimensional problem, which is this guy. So what we do in Stride is that essentially we try to alternate optimization over this problem with optimization over this to get a little bit of a faster convergence. The trade-off is that this is convex. So if you do local optimization, you get to globally optimal solution, but the convergence might be slow. And instead, if you do local optimization on these, convergence is actually very fast. You can do very fast interior point methods, but this can converge to local minima. So maybe one way to understand Stride is that we do local optimization over this, and whenever we are stuck in a minimum, we try to escape the minimum using the SDP. That's maybe a good way to describe it. And just to clarify, these are great questions, and of course, it's much beyond what I'm covering in the slides. Look at the paper for Stride. I think we have cool ideas on solving this faster, but even Stride is getting us to solve these in seconds is not real time. Full disclosure.
There is one question in the Zoom chat. So it's asking about the certification step. Suppose we cannot certify the quality of the estimate. Do you have suggestions on how a decision-making algorithm should treat such a scenario? When we cannot certify the estimate of a car is posed, do we stop or continue assuming there's no car?
It's a good question. I think there are two cases in which you cannot certify. There is a case in which maybe your algorithm, there is a case in which the relaxation is tight. So the relaxation is tight, but maybe your algorithm is I think that's a bit complicated. So the relaxation is exact, right? But maybe you're not solving exactly the relaxation, and therefore, you're stuck in a bad solution. In that case, Stride again provides a way to escape this local minima. So Stride, which is this SDP solver that we have, will provide a way to correct your estimate to get it to optimality. But there is also a second case, which is what you're referring to probably, which is the case in which the SDP is not exact, right? So the good news is that this case in practice is very rare. You use typically for all perception problems that you care about with a reasonable number of outliers, this relaxation is going to be exact, which is really one of the most impressive findings of this work. If it is not tight, what happens is that you solve this optimization problem, you get a solution, and the solution is not rank 1. In that case, really depends on the task. If you're doing a very safety critical task, maybe you want to reject the solution and really trying to stop the car or just to have some mitigation plan. The good news here is that whenever you have a rank 2 solution or a rank more than 1 solution, This problem can still provide a suboptimality gap. We still quantify how far you are from the optimal solution. So maybe you can use that information to say, look, if I cannot get an optimal solution, but I'm quite close to optimality, maybe I'm still okay. If instead the suboptimality gap becomes very large, maybe I want to stop my car and I don't want to trust the estimate. Yeah, so it's a long answer, but I think really depends on your application.